We present QuikDeform, a robust and relatively fast Maya plugin for physically based animation. As you can see, QuikDeform works well for giving elastically deformable behavior to both volumetric meshes and thin shells. When we began working on QuikDeform, we had two initial goals. We wanted to give this rich elastic deformation behavior to volumetric solids, thin shells, and cloth, but also we wanted to allow an artist to strongly control this deformation through a variety of constraints and parameters. We had time to implement three types of constraints in QuikDeform, the first being a position constraint where we simply hold a point constant, and the second and third are 3D and 2D strain constraints where we either limit the strain on tetrahedrons or the strain on fragments. So that's the difference between volumetric and thin shell deformation. Finally, we wanted to give artists control over which constraints to add, so that's just among those three constraints, what constraint parameters to add, so like what constraint weights, what simulation parameters they wanted to add, mostly relating to the simulation itself, so solver iterations, time step, number of frames, etc. And finally, we allow the artist to define some collision planes and their corresponding frictional damping coefficients. As for our technical approach, we were inspired by a 2014 SIGGRAPH paper on a simulation framework and algorithm called projective dynamics. This work's core goal is to perform fast, accurate, and robust physically based animation in real time. The paper itself has two main components, a local global solver and a set of continuum mechanics-based constraints. In this way, projective dynamics is somewhat of a hybrid between position-based dynamics and the continuum mechanics-inspired finite element method. So what does QuikDeform do well? As you saw from the title slide, it can provide rich elastic deformation for both volumetric meshes and thin shells. We achieve this using the classic co-rotated elasticity model for 3D strain and a two-manifold projected version of this strain in 2D. Additionally, the users have some really rich capabilities within the QuikDeform Maya node. A user can choose external forces like gravity and wind, as well as defining the aforementioned collision planes by simply clicking on planes in the Maya environment. Unfortunately, these are currently restricted to horizontal and vertical planes, but we found this is sufficient for now. Finally, a user can point and click on specific vertices to constrain them during simulation using our point constraints. Unfortunately, due to time constraints, we do have some areas that we believe need more work. The first is that we did not have time to implement a bending constraint, and as such, when we try cloth simulation, it appears rubbery. And furthermore, we used some simple hacks for collision detection and resolution, and as such, we do not have any robust general collisions or self-collisions. Unfortunately, projective dynamics itself even has issues with collisions because it can greatly reduce the performance of the global step during runtime. We'll now take some time to show off some demos. For our first two demos, we wanted to show the workflow in Maya for an artist as well as the results. Our first demo is Space Jello, and so we seek to show how a user can bring in a few planes and a cube primitive and have that bounce around and elastically deform in a box. Here you can see we've already clicked on the mesh, and then we instantiate a QuikDeform node by clicking on the menu option, bringing up this little pop-up window. In this window, you can see that we have a lot of options, all of them either simulation parameters or constraint parameters. So for example, we're trying to change the initial object velocity here, and you can see you can define the x direction, y direction, and z direction. And finally, we can actually add our planes as our collision constraints to the system by just clicking on them and then clicking add, and you can see now they're all in that collision constraints section of the GUI. Finally, we just toggle gravity to be off, and once we're happy with these parameters and constraints, we can just press simulate. Once simulation is completed, we can just use the time scrubber in Maya to actually iterate over the frames of simulation. So you can see that happening here as the Jello cube moves through the space. For our second demo, we wanted to show how an artist using our plugin in Maya might be able to actually take advantage of our thin shell deformation that we've added. So as you can see, we've so far added a cylinder as a flagpole, and we're trying to make a waving flag with a wind vector. So once we're happy with our Maya primitive plane and the subdivisions on that, we can again instantiate the QuikDeform node. Just make sure that we pick thin shell deformation this time, and again adjust parameters. Additionally, we can actually select individual vertices to be added as position constraints, so those two positions of the flag will be constrained to be constant over time. Additionally, this time we want to actually include a wind vector, so as you can see, you can define the direction, magnitude, and the oscillation of the wind based on the amplitude and period of a sine curve that varies the wind with time. And once we're done, we click Simulate. Once simulation is complete, we can just press play on the time scrubber instead of dragging this time, and you can see it in motion here nicely. For our third demo, we wanted to show how the artist can actually change the Young's modulus to get different deformable behavior. So a low Young's modulus, you'll get a little bit more elastic deformation, like on the right. We also experimented with the effect of keeping the user-defined original mesh versus using the TetGen mesh, so using the tetrahedralized mesh that TetGen spits out, and then finally comparing a Maya subdivided mesh and then keeping that original mesh. And you can see them from left to right like that. So you can see that if you subdivide in Maya, you can actually get richer, more robust behavior. For our fourth demo, we wanted to do a similar Young's modulus comparison, but for thin shell deformation. And as you can see, as we go left to right, we increase Young's modulus and therefore decrease the amount of elastic behavior that we see as a result. Finally, we have two quick renders to show that we made all within Maya using QuikDeform. Our first render is Superman's cape, showing off our thin shell deformation paired with our wind oscillation. Our final render is, of course, a wacky waving inflatable arm flailing tube man that shows off our volumetric mesh deformation paired again with the wind oscillation. Thanks for watching, and you can check out QuikDeform at the GitHub link below.